Well, welcome, ladies and gentlemen. This is an inaugural lecture for Durham University, today presented by Professor Stephen Lindsay. I've got a little introduction to Steve, which I'm going to read. We're always privileged to have inaugural lecturers, but Steve is particularly special because this is his second one, and the reason for that will become clear. So Steve's first degree was in applied zoology at the University of Wales, and he went on to study for his PhD at the London School of Hygiene and Tropical Medicine before launching his research career working at the UK Medical Research Council's laboratories in the Gambia. Since then, he's worked at the University of Glasgow, the Danish Bilharzius, I'm sure I said that wrong, but I'm sure you can correct me, laboratory in Copenhagen, before joining Durham University for the first time in 1996. He was made a professor at Durham 10 years ago, and after a short break at the London School of Hygiene and Tropical Medicine, he rejoined Durham University in March 2012. He now holds a new chair in biomedical entomology in the School of Biological and Biomedical Sciences, so hence the second inaugural lecture. He is also an honorary professor at the London School of Hygiene and Tropical Medicine. So please join me in welcoming Professor Steve Lindsay.
This is fantastic because it was working. I've tried this about 6 times. It was working perfectly. Now it's not. There you go. Well, thank you for turning up today on what is a pretty inclement evening. So for those of you that have not been to an inaugural before, this allows me the opportunity to tell you something about one of the areas I do research in, but also to tell you something about my travel through my career and how I got here this evening. So what I'm going to talk about is explain, assuming you know nothing about malaria, and then tell you about where we are with the success of malaria control, and also my fears for the future, and try and weave in some of my research into that theme. So I thought, knowing that there'd be a number of students here, I thought I'd better tell you where I started out. And I'm a complete failure, actually. So I wanted to be a vet originally. I couldn't get the A-level grades, but interestingly ended up lecturing to vets during my career. I went to university to do wood science, would you believe? Extraordinary. And I ended up here. But what changed my career plan was sitting down one Sunday evening and discovering an exam paper in the subject of applied zoology. It was all about diseases of livestock. I thought, oh, well, that's a bit like veterinary science. Let me do that. It was more than that. It was about diseases of humans, a lot of tropical diseases, and the diseases of agricultural importance. And this sort of wide perspective has always shaped my thinking. I also have this unbelievably bad habit of saying that, or doing the most inopportune things at the wrong moments, and this is just an example. I went on to do a PhD in clinical pharmacology and gave up after 6 months. And the important thing here, folks, is to do something that really grabs your imagination. And what has always grabbed my imagination is tropical medicine. And so I eventually got myself to Keppel Street, here at the London School of Hygiene and Tropical Medicine, and became a research technician, a lab technician, injecting drugs into rats. And then I started my second PhD on the immunopathology of lymphatic filariasis. What's the way the body responds to lymphatic filariasis? What's lymphatic filariasis? This is lymphatic filariasis, a disease which affects millions of people around the world. It is a disease transmitted by insects, by mosquitoes, that they spread this infection. Now, I didn't really understand much about immunopathology, but I got really excited by thinking about mosquitoes, because for me, it's like being a medical detective. Who done it? The mosquito did it. And For me, it's about getting inside the head of a mosquito to understand how to control it. So I was given the responsibility of running the insectaries. I was very good at that, and a lot of my mosquitoes escaped. And if you ever go to the London School, you'll notice that there are bus stops nearby, and underneath the bus stops are the insectaries, where occasionally my mosquitoes would get out and bite people at the bus stops. But that's another story. And once I found one of my mosquitoes on the tube, but don't tell anyone. Now, at the front of the London School is this very marvellous badge, and just above the badge is 2 golden insects. And we show them closer here. Both of them are mosquitoes. The one on the left is a mosquito called a culisine mosquito. The one on the right is the one that transmits malaria. Now, why are we worshipping these golden insects? Because they're important. Here's a list of diseases which are transmitted by vectors, animals that transmit diseases from between people. These diseases occur in a lot of different countries and are hugely important, sort of the attrition rates here. Not only causing death, but a lot of blindness, a lot of morbidity, a lot of sickness, in other words. Now, there is something peculiar about vector-borne diseases, and this is best illustrated by this concept which is called the R0, the basic reproduction number. This is a very simple thing to understand, but it's complicated mathematics. So imagine that I have an infectious disease. Many of you in the audience will think that's not so difficult to think about. So if I have an infectious disease, in order for the disease to become stable, I have to infect at least one of you in this room. So that's a R0 equals 1. And if I don't infect anyone in this room, the disease will disappear. So if you look at these values for R0, these are all infectious diseases caused by or transmitted by coughing and spluttering, whereas these are vector-borne diseases, and you can see there's a logarithmic order of difference. These vector-borne diseases are a very special suite of infectious diseases. So if you're a pathogen, getting a lift on board a vector makes it far more efficient to transmit. And many of the emerging diseases that we're encountering today are vector-borne. So what about malaria? Because it's at the top of the list and it's the most pathogenic. Essentially, it has 2 cycles. One in the mosquito, the Anopheles mosquito, the one that sticks its bum up in the air. So the next time you're in the tropics and you get bitten by a mosquito, look for the one that sticks its bottom up in the air. That's an Anopheles. And the other extremely complex cycle goes on in humans. So it's a protozoan, a single-celled animal. There are 5 species in humans. When I was here 10 years ago at my inaugural, it was 4 species. We found another species. It's a monkey malaria, which spills over into the human population, found in Southeast Asia. And we're just beginning to uncover what's going on in that life cycle. It's almost entirely infections of people, and it's transmitted by these mosquitoes, the one that sticks its bum up in the air. And the best vector of all is Anopheles gambiae. Where is it found? It's grounded in most of Africa. This is its heartland. This is where it's really entrenched. And who does it affect? Largely children, under 5s, pregnant women. And so my launch pad from London School of Hygiene, and it causes a lot of deaths, was to go to the Gambia. Now, before that, I want to make the point that 25% of childhood deaths in tropical Africa are caused by malaria. Now, this is a group of British school children from a school which is very close to here, actually. These are English kids. If they were born in the Gambia, those children would be dead from malaria. They wouldn't have gone past their 5th birthday. This is an infectious disease which is entirely preventable. This is unacceptable that we allow that to happen. So, suitably impressed by these numbers, I went to study in the Gambia, and I spent 6 of my years of my life in a one-horse town in Farafenni, which was full of prostitutes and people selling fabrics. It was an interesting place to be, I can tell you. This is Farafenni Field Station. This is Walikunda, where I used to do a lot of my work and still carry on doing my work. I keep on going back to the Gambia. It's a very hot and uncomfortable country. It's very difficult to get anything done, but it's a great place to do research. Now, there's two important things about the Gambia. First is it's the home of Anopheles gambiae. Remember I said this is the malaria vector, which is the most efficient vector in the world, and it's actually named after the Gambia because it's where it's first found. The second thing is there was this remarkable gentleman here, Sir Brian Greenwood, who was the director of the institute at the time. He was a real bugger to work for, but he was an extraordinary man because he had two simple things that he wanted to do, which was revolutionary. It sounds simple now, but at the time it was revolutionary. And that is, first of all, to find out what children were dying of in the villages. Go into the villages, find out what they're dying from. Secondly, do something about it. And it was that sort of sea change that which really started my career. So how do we protect children against malaria? Now, at the time, most of the people in rural Gambia, and unusually for African countries, were sleeping under one of these, a mosquito net. Not like made of netting, but of sheeting. And we thought, great, we're going to protect people by sticking insecticide on it. Permethrin is what we used. And so what you can do here is you dunk a capful of insecticide into this bowl, and this is a cap which contained milk. Add to this 1 litre of water, mix it into this white solution, dunk your net in there. At the beginning of the rainy season, that's it. Dry it out in your bed, it'll kill your bed bugs, which it does remarkably. Now, we did this very large study. This is summarising 4 years of work in villages where they just had untreated nets, okay? So this is untreated nets. And what we're looking at here in these villages is deaths of kids towards the end of the rainy season. So this is the rainy season. Most of these deaths are caused by malaria. So this is year 1 and that's year 2. Now, we had another group of villages in the same study area where we also recorded their mortality. And this is the first year. So we're just showing here that there's similar pattern in mortality between the two groups of villages. But in this group, the second group, we dunked their bed nets with insecticide at the beginning of the rainy season, and you can see there's this deficiency. There's no kids dying here. Now, this remarkable result was picked up by WHO, the World Health Organization. Copycat trials were carried out to show that these were effective. Now, we don't dunk anyone's net in insecticide now. The idea was picked up by industry, and what you've got here is a $5 net which is impregnated with insecticide. You can wash it numerous times and it still has insecticide on it. It would last 2 years, 5 years and still leak out. So one of these can protect you against malaria, and it's a highly sophisticated piece of chemistry in that net. But overall, it reduces it by 50%. So that's fantastic. So my talk is titled Malaria Control, the Success. Well, what's the success? Well, over the last 10 years, these nets and indoor residual spraying has been rolled out across Africa. So 145 million nets of those nets have been distributed in 2010 alone. 153 million people were protected by spraying in Africa. Now, this big umbrella organisation, Rollback Malaria, is a grouping of 400 different bodies. So these are national malaria control programs, the World Health Organization, industry, anyone that's involved with this. And I'm chairing one part of Rollback Malaria and providing them with information, technical information. But extraordinary that we've reduced malaria deaths by 33% over the past decade in Africa, and globally by a quarter. That is utterly extraordinary, because 10 years ago when I was standing here, I wasn't believing the stories of the decline of malaria. I've been used to malaria being very stable, and from year to year I've lived with it. It was about malaria control. This is malaria declining. We've saved well over 1 million lives so far, 274 million cases of malaria averted. But there are still a lot of deaths, 600,000 deaths occurring in Africa each year. That's a huge number of deaths. This is a major public health triumph that very few people, I guess, in the public know about. Here's an example. This is malaria coming down in Eritrea as insecticide bed nets go up. This is in the Gambia. You can see that malaria is sliding down here in dark blue. Malaria deaths in Sibonor, which is near the coast, declining, as is all causes of deaths, because malaria contributes to other deaths. It's malaria and diarrhea. It's malaria and acute respiratory infections which kills. You take malaria away, you have a profound effect on the other diseases. Now, with this excitement over the last 10 years, people have started to move the goalposts and not talking about control. And these two good people, Bill and Melinda Gates, have invested considerable amount of money, and very cleverly they put the director of WHO into a corner at a major international conference and said, "You do agree that we should eliminate malaria?" To which she could hardly say, "Well, actually, let me think about this." And she said, "Yes." So there's a huge responsibility to carry on with this effort. So that's a success, and we should applaud that success. But what about the crisis? This is also a slide I showed 10 years ago, and the joke is, unless you live in a free school in the north of England or in Georgia, and if you don't understand that joke, I'll tell you afterwards. But what I'm meaning here is, whatever chemicals you use for controlling whatever infectious agent, there will be some organisms out there that are naturally resistant. And when you use this chemical over in large amounts, those that are naturally resistant will thrive and propagate and spread their genes to the population. So we've got 3 chemicals that we use for control of malaria. We've got this wonderful drug artemisinin, which comes from a Chinese herbal remedy, but is now the best ever malaria drug. We've got the pyrethroids on that net, and it's only the pyrethroids we can use on those nets because it's so safe. And then we can spray DDT or pyrethroids on the walls. Now here's the problem. This sent shockwaves through the world, but they clearly hadn't been to my inaugural lecture 10 years ago. This is what artemisinin should do. If you have parasites, it drops them really quickly, within 48 hours. This is why it's such a good drug for severe malaria, because you need to drop the parasites out of the body quickly. But here in Cambodia, we've got a problem. They're clearing much slower, which means that these people are more likely to die from severe malaria because of this delay. So it's the first indications of resistance in this population. We're doing a lot of work at the moment to try and squash that outbreak of resistance. But I think the genie is out of the bottle. Well, what about the insecticides that we use on our nets? This is an old diagram now, but in red it shows you where we've got resistance. We've got mosquitoes which are resistant to that insecticide. And that's out of date. All over Africa we can see red dots now. So the problem is, well, what else do we use if we get resistance? Well, we've only got 4 classes of insecticide that we can use for controlling our mosquitoes. Here they are, the organochlorines, the pyrethroids on the nets, carbamates and organophosphates. And this is what you actually find in practice. These are the field data here. So when you stick some mosquitoes in a tube which is impregnated with the insecticide, it should kill them all. But here they're not. They're surviving. Only in Burkina Faso, DDT only kills 3% of the mosquito population. It's useless. And the problem with this is you can get cross-resistance between different types of insecticide. So this is really worrying. And if you think that's worrying, if you go to Tiassale in Côte d'Ivoire, Ivory Coast, here are our 4 classes of insecticide. it should be killing them all, or at least 90% of the mosquitoes that we put on the paper. But they're all surviving. So unless you just throw the aerosol at the mosquitoes, you're not going to kill them with the insecticide. So that's one problem. Then the other problem is behavioural resistance. What we're doing here is sticking all our insecticide indoors, whether we're spraying it on the wall or putting it on the nets. So imagine that we've got an outdoor population and an indoor population of mozzies. What we will do, if we're effective, is reduce the numbers that come indoors, but we won't really affect those that are outdoors. And I'm going to show you some old data here. This comes back from 1971 with DDT spraying in the Solomon Islands. So here we've got our mosquito, and this is biting from 8:30 in the evenings outdoors, and it reduces during the night. And the same indoors. That's before spraying, and then after spraying, it changes its behaviour. You can see a lot of the biting is occurring outdoors early in the evenings. How do you protect people against outdoor early evening feeding? Really difficult. Really difficult. So that's one problem. The second problem is we're going through, unless anyone has been in another planet for the last 10 years, a global recession. So although funding to power malaria control has increased, it's now on the wane. And that's deeply disturbing, because what happens when you stop malaria control programs is visualized here. In numerous studies from around the world, this is when the red arrow simply marks when the program ended. And what you can see is a resurgence of malaria. So the message is, if you don't continue to control malaria, it will come back and bite. And that's the concern. So what do we do now? Well, I think we've got two scenarios. We're either heading for an iceberg, or we've hit an iceberg and beginning to sink. So the business as usual scenario is not to do anything. But for malaria control, what weapons do we have? I've spoken of only two. You spray insecticides on walls of houses, or you stick it on the net. So in some programs around Africa, they've been doing the bleeding obvious and combining nets and spraying together, but we don't know whether it works or not. Now, we, the larger team at Durham University, have conducted a very large trial, and thank you very much for everyone here for supporting it, because it's funded by British taxpayers to the tune of £1.2 million to do this study. We wanted to know whether there's any additional benefit of spraying the houses if you've got a net. So we had two groups of houses, those with nets alone, like that, and those with nets and spraying. And we did this in the Gambia, and we had 35 villages in each study arm. We followed 7,000 children for 2 years. It's a very large study, and we haven't yet written it up, but I'm going to show you the most important data that's coming out of this. And what this shows is the children that started our trial here getting malaria in the two arms. And it's almost unbelievably that there is actually no difference between the two arms of the trial. So what this is telling us, if a child sleeps under a mosquito net, there is no additional protection from putting the insecticide on the wall. So don't do it. Okay. So what else can we do? At the moment, our attention is controlling mosquitoes indoors. What about the outdoor population? How do we get at them? And people have just ignored that part of the program. What about larval control? Larval control has been extraordinarily successful in the early part of the 20th century. And there are many examples. And the example I'm going to give you tonight is the one from Sardinia, which was a real hotspot for malaria in Italy. People died from there in large numbers. And here are the guys in Sardinia trying to eradicate Anopheles labranchius, by letting the streams flow or using larval control. Very much what we're doing today in parts of Africa, or we've been testing. But So we know historically that larval control was successful, but does it work in Africa? People wouldn't believe it could possibly work. They said, well, Anopheles gambiae is everywhere, it's just too much. Don't even entertain it. So Ulrika Fillinger, who was at the time employed by Durham University, did this experiment, or we did the experiment together. And what you can see here is the numbers of mosquitoes coming into houses in black bars, and then we're larviciding with a bacteria which kills the mosquitoes. So it's a very safe thing. You could drink the bacteria, it wouldn't hurt you, but it's lethal to mosquitoes. It gives them something like insect cholera. So what she shows here is the numbers just disappear. The blue lines show the rainfalls to show that it's still raining, there's still lots of puddles around. And then she runs out of money, and then the mosquitoes come back. So that was a good indication that in Kenya we can actually control this mosquito. So the cry is scale up then. So there were 5 large trials that were done around Africa where we did this on a large scale. And I'm going to report on one of them that was done in the Western Kenyan highlands in the valleys. Now in the valley bottoms here, this is where all the mosquitoes are, breeding in the drainage channels, etc. People live up here. So we did 2 things in this study. We introduced bed nets and we introduced larval control. And the nets work. We know they work at reducing infection, 31% reduction. But the larval control, the larval source management, was also protective. And there's actually no statistical difference between these two, so I'm not worried about this. But the important message is if you use them together, you get an added protection. So that's the effort then, is integrated vector management. What else do we have to do? We have to do a systematic review. For any medicine that you use, you will, to know whether it's effective or not, people carry out these Cochrane reviews. They are systematic literature reviews. We went through every paper that had been published on larval control, and there are thousands of them. And what we showed is this. Now stick with it. It's not as difficult as it may appear, and I know it's late at night. So what we did was look at the effect of larval control on whether it reduced the risk of malaria. Now in these studies, these are pre-intervention, and all it shows is that the 2 groups, the group with larval control and without larval control, are similar. What we then show is that this value is less than 1. It means it's protective in this series of randomized trials. We looked at another group of studies before intervention. The villages in the 2 groups, larval control, no larval control, were comparable. After the intervention, they all dropped below 1. And overall, you can see that there's a big reduction, a 58% reduction in malaria with larval control over these studies. And this is the sort of information you need to influence policymakers. And then finally, we end up with this, a manual that I wrote or directed with my colleagues Ulrika Fillinger and Lucy Tusting, who's now at the London School, 10 years after doing the first experiment. So it's actually taken 10 years to show that larval control is protective against malaria in Africa, which is terrific. My other interests are, well, what else can we do outside the health service? I get terribly frustrated because when you deal with health people, and they're largely medics, and if there are any medics in the audience, actually I'm not going to apologise to you, but the point is, people that deal with health think you can solve every health problem through chemicals, whether you inject it, drop it into a tablet, spray it on the wall, stick it in a net. I think there are other opportunities, and one of them is mosquito-proofing houses. And this is one of my real heroes in life, Angelo Celli, who carried out the first trial against malaria. Now, when I saw this picture in his book, I thought this was absolutely wonderful. I thought it was a hayrick, actually, with a telephone kiosk outside it at first. It is actually someone's house. And they controlled malaria in parts of Italy by screening, amongst other things. And the best experiment that he conducted was on the railway lines from Rome. You know, Mussolini got the trains running on time. He did a lot of bad bad things, but he got them running on time. These are different railway lines, and what he did was get some of the people that worked on the lines in screened houses, wearing protective gear at night for mosquitoes. And you can see here the difference between the protected group and the unprotected group. So I think there was something like a 90% reduction in malaria by house screening. So we took that idea a bit further on, and this is my prop. This is my little house here. What you have to understand is there's something very special about our Anopheles gambiae, because when it flies above the ground, it flies about 1 meter above the ground, and when it hits a vertical surface, it flies up. And it's that behaviour singularly which makes it such a good mosquito at coming indoors. Most of them bounce off sideways, other species do. This one will go up and funneled in under the roof, because nobody blocks the eaves in Africa. You don't build houses like that. So that's how they get in. Now, we thought, great, we can use this, turn a house into a big trap. So you put screening along the top here. This is just no chemicals involved, just mesh. So that the volatiles that the mosquitoes use for finding their way into the house come out. The mosquito gets into the roof space but can't get down. So that was one of our, and we showed that simply doing that reduced entry of mosquitoes by about 80%. So we did this trial where we had a control group, no protection, our screen ceilings, and then what we typically think of as screening, screen up the doors and windows and fill the eaves in, that gap between the top of the wall and the roof. And this is what they actually look like. Here's our screen ceiling, and on the door here we've got a screen door, which has actually been painted by the person who lives there, because they really liked it, so he painted the door for us, and then we closed the screen. To cut a long story short, was this effective? It reduced the amount of malaria anemia, which is a killer of kids. Kids under 2 die of malaria anemia by half in both groups. It didn't really matter what type of screening that you did. And I would say that these results are better than you get with a malaria vaccine. And there are no chemicals involved here. So this is the sort of thing that one can do. So one of my major interests now is thinking about development as a tool for malaria control. And so we asked the provocative question, is development the most cost-effective malaria intervention? And this has started, I guess, about 20 years ago when I wrote a paper called Paddy's Paradox. Oh, it feels like 20 years ago. And Paddy's Paradox is this. When you get rice fields like this is a fantastic breeding site for Anopheles gambiae, our vector. But what was interesting and surprised me was that in riceland communities, they actually had less malaria than surrounding communities. And I thought that was intriguing. And so here's my hypothesis, that rice production increases the wealth of the farmers, and that wealth is protective in its own right. And how wealth works as being protective is still a matter of some conjecture. But I would say it provides use of a bed net, it provides better quality housing, better nutrition, better access to healthcare. And essentially what I'm talking about here is development, if people earn money. And there is this complicated arrangement between malaria and development. We know that countries that have a high amount of malaria, their economic productivity is reduced. Indeed, the argument for scaling up malaria intervention in Africa was an economic one, because they argued if you put in X billion dollars in, you'll get 3 times as much out because you'll increase the productivity, we've got new markets to sell to. So you can argue it entirely from an economic perspective. So malaria limits development, but I'm also taking the view that development can reduce malaria. And so, just to give you a flavour of this is some of our research that was published in The Lancet earlier this year. This shows the probability of kids dying from malaria, and each spot represents an African country. And we've got this Human Development Index, and you can play around with these indices on the web if you like. Anyone can do this. But what it shows you is the better the development, the less malaria deaths you've got, which is really just arguing at a large scale. And we carried out one of these risk factor surveys rather cheekily, because these are usually used for looking at interventions, as I illustrated earlier, with larval control. And what this shows you is not protection this time, but increasing malaria risk in the poorest of the poor. So each one of these represents studies that were done in different parts of the world, and overall it shows that in the poorest of the poor they're twice the greatest risk of malaria than the least poor. Now what we're looking at is communities that it's not the difference between someone living in an African village and someone living in houses like we do. These are poor communities. All of them are poor communities, but the poorest of the poor are twice at risk of malaria. So think of development, increasing money as a weapon against malaria. So here's my summary. So simple interventions, it's not rocket science, can save huge numbers of lives. Malaria has been beaten down for the moment, has continued to be beaten down, but we're very wary about what the future holds. We urgently need new tools to combat this disease, and I want to say that provocatively, that think about development as a way of reducing the burden of malaria globally. And because I knew we would have lots of students here, just to give you a flavour, these are ex-Durham students. Lucy was a first-year tutorial of mine. She did a literature review with me, and then coincidentally we ended up in the London school, and so she beavered across to my office and she did another project with me. And her first paper was published in The Lancet this year, and she'd helped me write without her, the number of studies would have been impossible. And here she is in WHO Geneva taking minutes of the meeting, and I'm supervising her PhD at the moment. She's in Uganda. This is Dr. Vanessa Chen-Hussey. I don't think any relationship here to Patrick, but she was also an ex-Durham student, and there are countless numbers that I have the pleasure of meeting at conferences. So think of global health as perhaps an avenue you could explore in the future. Now, this isn't my work. This is the work of a fantastic bunch of people that do all the hard work. I just stand here and play the royal we, but these are the people that really matter. My local team is Anne and Rachel at the moment, but most of the folk are overseas, because that's the only way they can tolerate me if they're well away from me. This is Margaret in the Gambia that I've worked with for the last 15 years, Musa for almost 30 years, a whole bunch of folk in Kenya. This is Uli, who's based in Mbita on Lake Victoria, a beautiful place, perfect conditions, and a whole bunch of other things. This photograph was given to me by a Durham undergraduate because he said he thought that was me and that was him, so I thought that I'd include that. But there's a lot of other people involved as well. So thank you for listening. I'm happy to take a few questions.
So we do have a few minutes.